Right. So let's get started. Welcome back. Good morning. Everybody who is at the bar, I hope you're hanging in there. Right. So this is lecture 3 of PyOpenCL, PyCUDA, and all of that. And what do I have for you today? Well, we have some leftovers from last time that I want to go over. Then the main theme of today's lecture is cogeneration. So you've seen bits and pieces of that in Matt's lecture, but here I want to show you more or less in detail and show you with a kind of worked example about GPU reduction. I don't know if anybody's covered how to exactly do that. If not, you'll learn that on the fly. Then, of course, it's not just about generating bits and pieces of code. It's also choosing among them, right? That's the premise of autos here, where you generate oodles of different versions of your code, and you figure out, okay, maybe I want that one over there. But how do you find which one is that one over there? Therefore, you need ways of judging the code that you've just produced. And lastly, I'll show you a toy that I've created that I'm quite fond of. If someone wants to help me develop that, I think that would be great. Okay, so let's get started. Leftovers. Right, leftover number 1. Thank you, past self, for the reminder. I meant to show you the OpenCL Spec, which I think is actually quite well written. So this is a PDF. You can't see very much of it, but here over on the left, you see the table of contents. In my opinion, it's quite well written and it's quite readable, and it gives you a good idea of what the OpenCL standard way of doing things is. And then there are vendor documentation such as from Nvidia and AMD to supplement that. It first goes and explains basically first the architecture, how the system is built up. Then it explains the runtime. You obviously can't read all of that, that's why I'm pointing at it. Then it explains the programming language, has lots of details on that. This chapter is folded open. Numerical compliance, some other stuff, what extensions there are, and I find it quite useful. Right. Oops. Oh, you're welcome, past self. All right. Another thing that I want to keep mentioning, as it happens, as I was preparing for the lab, this occurred. This happened to be in the last lecture as the crashy puzzle on command queues, right? If you initiate a transfer from some host memory onto the device, you had better make damn well sure that the garbage collector doesn't get to that memory before the stuff is transferred out. So beware of Python's puny little kind of cute garbage truck. So given that I've fallen for this bug twice now, and it's cost me some time, I think I'll put something in to make that safer. But for now, we'll whenever you do asynchronous transfers, which you will be doing in the lab, you'll have to be aware of that. You don't get into any such races. Lastly, because Matt asked that question last time, since OpenCL specifies both explicit and implicit SIMD, who doesn't know what I mean by implicit and explicit SIMD? Right, cool. You guys are on it. I like that. So implicit SIMD is more or less the CUDA way. What happens is you have a workgroup or a block in CUDA terminology, and that gets spread across a relatively wide SIMD machine. So work item number 1, or thread number 1, goes into the first little ALU, work item number 2 goes into the second, work item number 3 goes, and so on and so forth, right? Intel machines, on the other hand, work quite differently. They work by having you specify these wide SSE instructions and say, okay, do this with a vector of 4 things. Like add 4 vectors together or something like that. And the first way, the CUDA way, where the SIMD isn't explicitly encoded, but it's kind of implicit in the structure of your workgroup. That's what I call implicit SIMD, whereas the Intel way, where you say, okay, I have a vector of 4, that's what I call explicit SIMD. Right. And Matt was complaining and whining that OpenCL exposed both implicit and explicit SIMD. And my reply to that was, well, there's a feature that lets you have the compiler help you in assembling things into explicit SIMD if that's what the architecture is like. And what does that look like? Well, there's notation that looks like this. So you have kernel, and you say attribute blah stuff, and then you declare your kernel. And one of these attributes that you can specify is vec type hint. So vec type hint float 4 tells the compiler that the main unit of computation in your code in this instance is going to be float 4. And if it compiles that for an architecture like, would it have occurred Larrabee, that has float 8 as the basic unit of computation, the compiler would have attempted to glue 2 of these things together to form those 8 wide vectors. And if the SIMD instruction set of the processor is sufficiently complete, which in the case of Larrabee or these AVX instructions, it would have been, then that's actually perfectly possible. As in, it's a very mechanical task to write those explicit SIMD instructions. So it's not something like the compiler magic that was necessary for SF. Another attribute, so while we're at it, that you might want to know about is required workgroup size XYZ. Why is that useful? Can someone imagine why that might help? Any ideas? Well, it's obviously about giving the compiler extra knowledge, right? Whatever code you write is going to be valid and is going to run no matter if you have that in there or no. So what difference does it make? Well, suppose you have, get local size or something in your kernel, as in you query on the fly how big your workgroup is. And if you have this directive in there, then this evaluates to a constant at compile time. So the compiler can carry out that multiplication potentially much faster, and it can make all kinds of optimizations on the access pattern because it knows how many work items there are. And this is helpful for that. It can also make decisions on what register use is going to be like. It doesn't have to, if you have very few work items in your workgroup, for example, it doesn't have to squish as much on the register pressure end. So, yeah. Statically defined array, not really, because this has nothing to do with the data layout, just like the computation layout, the grid, and workgroup size have nothing to do a priori with your data layout. This is just something that. Right. Yeah. Okay. All right. So these two things are available, and there are actually a bunch more. And where do you find them? You find them in the spec that I just showed you. But in my opinion, these two are the most useful to know about. Right. Another holder from last time is I meant to talk about different OpenCL implementations. I'll talk about the dominant ones, let's say Apple and Nvidia API. Not in that order. Start with Nvidia, just because that's where you guys come from. That's what you already know. It's pretty much identical to CUDA, as in the model is identical to CUDA as we've seen. It's just that a few things have been cleverly or not so cleverly renamed. There's no native C-level just-in-time compilation in CUDA. Possibly that'll get fixed. So far, a nice convenient way to do that is to use PyCUDA. Sorry, I had to slide that in there. Then have you been told about what page-locked memory is? Who knows? Nobody. That's great. So in a nutshell, page-locked memory is memory that the GPU can get to without asking the host for help. So it can do asynchronous transfers without having to wait for anything. That feature is available in OpenCL as well. It's kind of hidden, but when you need it, well, you'll need it in the lab. That's what I'm telling you now. It's hidden behind this CL mem alloc host pointer. So it's kind of weird in that already has a meaning, and that meaning is not give me that kind of memory. The meaning of this strictly is give me a chunk of memory, give me a buffer that is accessible both from GPU address space and from host address space. It just so happens that if you do that, then you necessarily also get page memory. That's how they chose to jam that in, and they document it so they can say that. And as I said, you need page lock memory for genuinely overlap transfer. So if you mean to overlap computation and transfer. One feature that I've talked to David Lupke of Nvidia. One feature that Nvidia regrets putting into CUDA is texturing from linear memory. More or less consequently, I guess that's why this feature is not in OpenCL. So, but if you're looking for it coming from CUDA, it's just not there. But this is an intentional thing on part of Nvidia, as far as I understand. Also, if you guys are fond of the CUDA device emulation mode, as in where you can run your CUDA code on the CPU and go through it with a host debugger and printf and whatnot, if you like that, well, that's been taken away. But you can use a CPU implementation in CL just as easy. You have printf and you can use a debugger just as easy. And it's fast in terms of the host implementation. So I find that helpful as a debugging tool. Nonetheless, before I talk about the AMD implementation, I'm going to talk about the Apple one. Because Apple has to be different from everybody. Instead of CL/CL.H, if you program it from C, you have to say OpenCL/CL. Kind of confusing, but you'll get over it. And instead of -L OpenCL, you say -framework OpenCL. Also, they have another misfeature in their implementation that you might be tripped up by. They have a compiler cache, as in if you compile the same piece of code multiple times, then they're smart enough to say, oh, he's just recompiling the same thing, we'll just give him the same binary. Except it's quite not perfect. If you include files, it just ignores them. So if the include files change, it gives you the same binary. There's a way to get rid of that cache or turn it off, or flush it every time that you change it. But this can be quite hard for debugging. People in my class at NYU ran into that. Then, Apple supplies an implementation for both CPUs and GPUs. So you'll see one Apple platform, and then underneath there you'll have CPU compute devices and GPU compute devices. And for a CPU, the mapping, the way that the grid should map onto processors is not entirely clear because, well, each individual CPU, each individual core is not that terribly wide, right? And Apple has decided that it would expose that as mapping just exactly one work item to each core. Whereas, as we'll see, the AMD implementation lets you use more than one work item per work group. So, one work group maps to one core, if you recall. And then the question is how many, what's the limit on the work group size? As in how many work items can you have per core? And for Apple, the answer here is 1. And for AMD, it's multiple, and they do smart things to map that down. The GPU implementations here are relatively similar, but well, I assume they're the same code as the GPU vendor implementation, so there's not too much to say here. Also, here's an interesting political tidbit. Intel reportedly doesn't like OpenCL. They really want to push their own stuff. They've invented CTC for throughput programming or something. Yet, with their new chip, Apple apparently strong-armed them into implementing OpenCL. So they can if they want to. You just have to push them to release that also on other hardware. Lastly, the AMD implementation. On the GPU, these GPUs from AMD, if you have very flop-heavy workload, those might be worth checking out because the machines are super flop-heavy. So, in terms of core count, they're just about as wide as Nvidia. Yet, so core meaning instruction fetch, how many instruction fetch units there are. Yet, each individual core has a pile more floating point power. How is that exposed? Well, each work item maps to one execution lane, and then each execution lane itself is 4 and 5 1. If that's out, so that would be the part that you would talk to through vectors, through this explicit SIMD part of OpenCL. If that sounds horrible, well, if you're memory bound, you're likely not going to be making use of all those flops, so you can ignore the extra SIMD width and still be okay. But in essence, there's both implicit and explicit SIMD, and thus it makes sense that that stuff is right. And as I said, in the CPU implementation, you can have multiple work items per work group, and they somehow emulate that. And ideally, they'll map it to different lanes in SSE code. And they have print as an extension that you can use like as I explained. Right. Cool. That covers it about for the holders from last time. Are there questions on what I've said so far? Yes?
So when you said you can use AMD-CL instead of emulation mode,
Mm-hmm.
do you need a AMD processor?
No, you don't. They let you use whatever processor you bring. All right. Okay. So that just about does it for from last time, about what we left over from last time. When did I start? I'm just trying to gauge where I'm with respect to time. 25. Okay. All right. That's good. Then let's move on to the next big thing of today's lecture, which is code generation. The idea behind code generation comes from, well, having to adapt code to different situations. Turns out that CL can talk to quite the variety of stuff. It can talk to multi-core GPUs, it can talk to various GPU architectures, it can talk to accelerator boards, if you have one of those. And all those devices differ by things like memory size, latency, well, you can read yourself, right? And optimally tuned code won't necessarily look the same on all those devices. So obviously, well, you can say, and then I'm going to just, for each and every individual device, I'm going to write my own code. I'm going to have it tuned and all nice. But that's a waste of your time. Because, well, then you have to sit down and do all this work yourself and figure out how to make the code adapt. In my opinion, a better idea is, if you are in the setting where you are scripting a GPU, there is no such thing as a compile time. So there's no such thing as a compile time constant. In particular, the GPU code is not a constant, because there's still compile time. So you can generate that as you go along. This folks had that right even, like 40 years ago. Code is dated. It wants to be called that somehow by other code. Hopefully not by itself. That was Lisp GPU. Well, see, there might be a niche there. I don't know. For now, I'm happy with Python or Python for GPUs. Right? So well, you come up with an idea of different varieties of code that you might want to generate, and you pour that into Python code. That Python code generates GPU code, then that goes to a GPU compiler, ends up as a GPU binary, that gets executed by the GPU, and you get a result. Oh, long string stuff that needs to happen. Fortunately, all this down here, taken care of by the machine. That appears your job. And I'd argue, people are reasonably good at both of those. In particular, Python is a pretty good way to do text processing, which code generation boils down. GPU scripting, well, you can do in PyCUDA, PyOpenCL. What might be a couple of other reasons why you want to machine generate code? Well, automated tuning is kind of the big obvious one, right? You want to generate different varieties of stuff. But it's actually a good idea for a number of other reasons. For example, if you're a library writer, then the user might ask you for a lot of different stuff at runtime that you can only partially foresee. For example, they might give you different data types, and they might give you one day a complex, the other day a single precision, the next day a double precision, or combinations of those. And if you want to instantiate all of those, say by templates ahead of time, then you're wasting a lot of time preparing for eventuality. Whereas in the code generation setting, well, you get asked to do stuff, and you just generate the code right then and there. And it's really just for this one purpose, and after you're done with it, you toss it out. More general way of looking at the same thing is you can specialize for a given problem. So if you've written libraries before, then you've probably encountered the problem that you want to allow flexibility at a point where that's in a very, very tight inner loop. Bringing flexibility there is kind of hard because, well, what are your options? You can have a function pointer, say, but function pointer jumps and inner loops are bound to kill you. If that loop has to run at any significant speed, then more or less every time that you call through this function pointer, or equivalently a virtual function, then what happens is the CPU jams into that jump, has to flush more or less its entire pipeline, wait, jump over, and do the same thing on return. Much better if there's straight line code, and in code generation, well, the stuff that you want in that inner loop, well, you stick it right there. No virtual function calls, no nothing. Another motivation is, well, as we've seen already before, giving the compiler knowledge that it might otherwise not have is an advantage. For example, with this block size, but also other ones. And constants are generally better than variables in terms of register pressure. Also, if you know a loop trip count, it's easy to just unroll that loop to that length, and it's usually faster than having any explicit flow. So it's probably a good idea. How do we do it? Three main ways. First one comes built into Python. That's just simple string replacement. And I'll show you examples of each of these. The next you've already seen from math, but I'll show you a clearer example of how that works. And then lastly, if that floats your boat, you can build a syntax tree and then have that generated the code if you need real total flexibility of substituting stuff into your code. We'll later talk about how to evaluate these different codes that you might generate. Before we move on to exactly how all this stuff is done, briefly, I want to push your brains into a direction. This means that the codes that you write look kind of fundamentally different from the codes that you might write if you want just one language. Say conventionally you might have said, okay, let me pick my favorite out of C, C++, Fortran, and all of those are kind of more or less good compromise on the performance to flexibility trade-off. Here you're choosing two languages. You're choosing one that's ultimately flexible, that's Python, and you're choosing one that's ultimately performant. So in that sense, you're not trying to jam one language into two purposes. You use a language for each end of the equation. That way, scripting for brains and GPUs for the inner loops. They're kind of two different purposes, and that way you exploit the strengths of each of those sides. I think this is a reasonable way to construct codes. Matt seems to agree, apparently. But consider it next time you start a code. With that, let's look at a few examples of how runtime code generation can help you. The way that I want to introduce this is through features that are in PyOpenCL that are, in my opinion, helpful in their own regard. So this is also more talking about what PyOpenCL can do for you, in addition to demonstrate how code generation can be used. What is there? Well, you've seen this at the end of the first lecture already. There's a data type called array. How many of you have played with NumPy? A fair bunch of you. How many of you have played with MATLAB? Okay, I'm guessing that's just about all of you. Okay. Pretty much the idea is to give you an object that is an array, just like MATLAB or NumPy, that you can do simple linear algebra on. So you can take a NumPy array. NumPy is, MATLAB for Python. That's a rough amount. So you take a NumPy array and you turn it into one of these guys by saying PyOpenCL.array.toDevice, and then you can do all kinds of stuff with it, add, multiply, take signs, ranges, and nearly all the functions that OpenCL specifies. You can mix types arbitrarily, so int plus float gives you float 32. You can print stuff for debugging, and you can still get to the raw bits and run your own kernels on these guys. So I'd argue many things that you might do on GPUs end up being vectors of some sort, and all the operations on that you don't have to code explicitly anymore. So this is the example that you saw. You take an array of random numbers, you transfer it to the device, and multiply by 2, get it out, and easy one. Any idea why cogeneration might be helpful for this? Since that's the angle that we're coming from. Yeah. For example, yes, data types are a good example where I can just, I already put this in here as a hint. You might get funky types from the user, and foreseeing all those combinations is kind of hard. But here you can easily adapt to that. This is all of this functionality and arrays is actually built on top of a facility that solves an even more general problem. If you've used, say, a vector class in C++ or a matrix class, something that you might have noticed if you evaluate a long nested expression, you can say x plus 2 times y minus z, and so on and so forth. What happens, what the library does, unless it's kind of smart and uses expression templates, you know what those are, then each time that each operator gets evaluated, a temporary array is created. And that can get kind of annoying, because the longer, the more deeply nested that expression is, the more temporaries you end up with, and the more you hurt for memory bandwidth, because each of those temporary arrays gets written, read, thrown away. So there goes a lot of your memory bandwidth. So that's a waste. And here's an easy way that PyOpenCL lets you circumvent that. So you import a facility called Elementwise Kernel. You feed it a context. You feed it something that looks like a C argument line. So float, give a scalar float, an array of floats, a scalar, another array, and output array Z. Then you give it one C statement that says what you want done to each individual item. And this thing then, when it's invoked like a function here, so then is an elementwise kernel, and you can call that just like a function. That takes care of figuring out a suitable layout of work groups and grid sizes, and running this partly in sequence, partly in parallel, so that it executes efficiently and does all of that for you. So how does this solve the problem that I mentioned with temporary creation? Well, there are no temporaries here. The only temporaries exist in register space on the GPU itself while it's evaluating that expression for each individual entry. And yeah, question? Yes, of course. This is something that only works for things that are embarrassingly parallel in a sense. That said, if you're careful, you can depend on other indices here. But you have to make sure that you don't go out of bounds and stuff. So within reason, as long as you want to do something for each entry of an array, it can be expressed using that. More questions here? Question answered, by the way? Yeah. Right, and then at the end you fetch this off the GPU and check if it gave the right result, and it does. Great. So embarrassingly parallel, data parallel things are one common pattern. Another common pattern is reductive operations, say norms or scalar product. Basically summing things across a whole array. How does that work? Well, there's a similar facility there that's not just elementwise kernel, there's also reduction kernel. There you specify context, what comes out as the result of your computation. You have to specify a neutral element, then a reduced expression, which in this case is a sum, and this is specified in terms of just to abstract things A and B. and a map expression, which in this case is taking one entry of one array x here and one entry of an array y here. You multiply those two, and you sum the outputs of these two guys. What have I just implemented? Dot product. That's right. Not too particular, I guess. One peculiarity that you might be able to exploit, what you get out of it, is a value that sits on the GPU. So, for example, if you're using that, if you're using that output in a Krylov method in CG, then there's hardly a point of transferring that one scalar out of the GPU and then transmitting it back to the GPU for say, the vector math that conjugate gradients implies. So you can leave that guy on the GPU. That means that you have to do a few more, jump through a few more hoops to use that efficiently, but it's definitely worth it, not incurring this double transfer penalty. Right. Okay. So good enough. By the way, how many of you have heard of Google MapReduce? Yeah, good bunch of you, right? So this is pretty well. I'm not claiming this is the same thing. There's just a lot of technology that goes into MapReduce, but MapReduce, same principle. And this allows you to construct something like that. Right. Now that we've seen this stuff in action and how it can be helpful, and well, right. This works by having a pre-made chunk of code and then substituting this reduce and this map into the relevant portions. And we'll see that right down here in the case study for the reduction example. How can you do it? Well, if you have a chunk of code, say this little kernel here, this is actually the implementation of the or this is part of what goes into this Elementwise kernel. And you substitute different keywords into different spots in this kernel string, right? So up here you want to be able to change the name, so it's % name s for string. So these are like printf arguments, and except that they have explicit names that go back down to this dictionary at the end. Yeah, question? That's right. So the triple. Sorry, let me quickly interrupt. The triple quotes are nothing magical and have nothing to do with the code generation. They're just a very long string that can incorporate new lines. That's Python substitution. Right. What does the substitution is this % operator here, and I can give that just an ordered tuple. In this case, it works like printf, right? So I would say %s to take the first string, %s to take the next string, or I can feed it a map, in this case a dictionary, from names to values, and then whenever it encounters a pattern like this, where it says % parenthesis some name and type, and it looks in the dictionary and substitutes this value into this pointer. So is that clear to everyone? It's not magical. It's really just string substitution. So you could also just put some special string here and then do string search in this case. Make sense? Okay. That's the simplest possible way, and it's actually sufficient for quite a number of things. Surprising. You don't need much more fancy machinery. Yet, if you want more fancy machinery, you can always have it. So Matt already showed a slide of that. This is a templating engine. Templating engines are things that, for example, generate web pages, right? And how does this work? Well, for example, if you're making a web page and you have your carefully designed banner with the ad on the right that you want to show to each individual visitor on each web page, no matter what the content, then you don't want to copy that particular part manually onto each individual web page. Instead, you template it and you just substitute the actual content into the appropriate spot on the page. And to be able to customize things such as lists, then these templating engines have evolved to allow flow control and all kinds of stuff. And that's what we're exploiting here. What does that look like? Well, from Mako template, we import a class called template. We make one from, again, the triple quoted string, so we don't have to worry about new lines. And then all that happens is basically this gets executed once, not in terms of the C. So this is a little bit, what you have to be careful here, this is two codes intermingled with each other. Stuff that involves percents gets executed upon template creation, and everything else is just the regular C code that then goes onto the GPU. I can see that there's a face palm in row 1. Okay, you know, it's fair to be initially appalled by it, but it's a little bit dense, but if you want to generate code, the next option that I'm going to show is less appealing still. Where this is where you generate a syntax tree, and you know, in my opinion, it's starting to look like Lisp, where you at the end very much close down. If you ever met, if you want GPU Lisp, you know, you're getting close. So this here covers a surprising number of cases, and yet it's rather, at least it fits on the slide. You put it down. So how complicated can code be that fits on one slide? Right. So let's briefly go through it to see what's going on. So like in the previous example, we feed this template a number of values, and right here we do that by calling the method render of the template object TPL and giving it a number of values. So for example, the type name, we specify the value of float. The local size, well, suppose we have a variable local size that says what that is. And again, also the same thing for spread. Right. Then, what the templating engine does is just read this string from top to bottom and look for instructions that it understands. So just simple substitution happens just by saying $breaks, just like kind of like shell variable substitution syntax. This type name gets substituted for this here. In fact, what goes between these two braces can be any Python expression, so you can get arbitrarily fancy. You don't have to. Just a variable name does the trick. So that's how we substitute the type name into the argument list. Easy enough. Then we substitute in the local size and the stride of the thread into this index computation here. So these just put into numbers. And then lastly, we expand the stuff that is between these two expressions here. So the templating runs into here, see the percent sign, and it goes, I'm being talked to. And you see the for loop, and again to the end for, and just loops around this thing for the given number of times. So that instead of just having one expansion of this here, you have an expansion of this here however often that you want. So this is an easy way to unroll a loop without having to rely on the compiler maybe or maybe not doing it. Yeah, question?
You get back an executable from this? You get back source code that you had?
Oh no, this is really all just string processing.
Yeah, so you get back source code.
You get back a source code that then you manually feed to the CL program. What is these here? What goes in between those is a Python statement. So here we make a new variable, or we assign to the variable offset, whatever, so that we can have. Well, we could specify this wherever we say offset. It's easier to have that in variable, and so we can use that variable then again in the expansion that goes between them. Any more questions about this? Anyone find it?
So I just are these all the features that come in template, or are they
Yeah. What else could there be? There's
string replacement and group unroll?
right. Yeah. I mean, you have every control structure available that Python supports. I'm not sure you can catch exceptions in one of those. That might be a good thing, right? But you know, you could have while loops. You can have if. So you can also call a Python function in there that can give you more text that could go right in there.
But then when you get the source code back, you can check it and make sure it actually does what you do.
Right. So this gives you a lot of rope to hang yourself. It's a question of how badly you want to abuse it. Right? And we'll see, like I said, we'll see what, so the reduction example is just a tad bit longer, in my opinion not too much fancier, but it does at least have an if in it, for example. We'll see that. Well, how else would you generate code? I've already hinted at it. Well, here you can generate a tree of objects that represents a piece of C, CL kernel. CL require workgroup size, function declaration, values, and then you have a bunch of declarators, a pointer, const, plain old data, type, name. Huh?
Who used?
I'm embarrassed to say. At some point, I thought this was a good idea. That's what I'm showing you. But, maybe you don't want to go there. It was not easy to maintain. It became. You know, like people look over my shoulder and like. People, like I said, people look over my shoulders like, you're coding Lisp? Like, not quite. Yeah, that's a flat. Lack of oxygen has many consequences. No, compared to that, I think this is surprisingly sane. And I mean, you know,
only compared.
Yeah, as long as
only compared. I don't think it's that bad. So, who thinks this is bad then?
To be honest, I think both of them are absolutely dismally terrible notation. And that's what really goes well along this way. Everybody that thinks this is nice always.
I like it.
Thanks for your support.
This was maybe slightly like.
Well, yeah. Well, you know, no matter what you think of it, they're possibilities. I'm just here to tell you about possibilities. I have to say, initially I was kind of also appalled by it, but all right, you know, whatever you want to think of me, I'll leave that to you guys. Yeah.
But you're applying all your optimizations at this level.
Right. Right. Yeah. No. I mean, you could generate some code, and since it's just a string, you can do arbitrary more things to it, right? You could. The possibilities are endless.
Why not have 35 quote marks to start it off?
Well, no. Three quote marks. As I said, that's a Python feature to say disregard or include all the new lines that are in between.
I'd like to have 35.
Yeah, well, it's all a matter of taste. There's a genuine question. Yeah, not just bashing. Okay.
Can you think of a practical example which generating quickly text tree would be convenient?
Yes. For example, this, which is the implementation that goes, or this is what is behind the array, element-wise array evaluation. Precisely this code. I copied and pasted it right at PyOpenCL.
I mean the other way, where you create the syntax tree.
Oh, the syntax tree. I think that's barely justifiable. pretty much everything that you might want to do, you can do in this way.
So maybe you could implement the complex code manipulation.
That's what I thought.
Yeah.
Turns out all I need can be done in this way. And Don't go here. It hurts.
If you were trying to like do optimization, it would be easier.
If you do stuff in a heavily structured manner where you're actually generating code structurally, this might work for parts of your code. But constructing a whole thing like that is just kind of superfluous. I've stopped liking it. So, unlike you say you get used to anything, I've at least retained as much taste as. Right. Okay. So now you guys have at least a little bit of an idea of how stuff might work. With that, let's look at an example. But before we go to the example and to more Mako templated code, which you guys enjoy so greatly, what are we trying to do? Just sit at after element, just vector adds simple element-wise things. Next most complicated thing is reduction. What's reduction? Reduction is, as you've seen, apply a function to the first two, then another function to the result of that, and the third one, and so on and so forth until you've done everything. This is in Lisp or Python, a function reduce. The C++ guys, of course, had to rename it. They think it's accumulate. Fair enough. Oh, and Scheme also renamed it to fold. All the same thing. What does it look like as a tree? Yeah, well, you can guess that. This is by virtue of associativity of f, binary operation f, go to this type of tree, and that's what we'll try to implement. How do we implement that in CUDA? Or OpenCL? Well, we want to use this tree-based approach, but on the other hand, somehow we have these two scales on the GPU that we need to accommodate in OpenCL also, right? We have the work item, we have the work group as one scale. Obviously, the whole tree is not going to fit into one group. So we have to have one structure within a work group, and then we have to have another structure above the work group. How is that going to work? Well, here's a picture. How about we make one little tree within each work group, and then just pave the whole array with these little work group size trees. This goes down to another array that we can then reduce with another work group, list of work groups inside until we get down to just the one entry that we want. Right. Oh, by the way, this is stolen from Mark Harris, who I've heard claim that he makes this seem fancier than it actually is. And it's a pretty simple thing. Very nice slides, so they're convenient. Right. Okay. So how might this individual thing look like? Or what might that look like? Well, how about like this? What do? We load all our data unless it's out of bounds. Then we try to do this tree-shape reduction. And what does that look like? Well, we have a stride, so that's basically from the perspective of each work item, what you want to do is you want to reduce yourself and something that's off to the side of a certain amount. The off to the side amount is no. This is not the optimum. Yes, it is. Forget it. Sorry. Yes, this is how much off to your side you're going to look as your work item. So at first you reduce with your immediate neighbor, and then you reduce further away and further away and further away. So that looks like you start with 1, and you keep doubling until you reach the local size. And if by modulo you figure out that you're supposed to be active, so your immediate neighbor 0's immediate right neighbor doesn't have to do anything even from the start. And as this goes on, even to your work items have to carry out the actual reduction and the barrier, and at the end you store. And graphically it looks like this. So initially active are really on 0, 2, 4, 6, 8, which leads to divergence. And on top of that, which warrants the claim, the first example has market intentionally contrived this module that dreadfully slow. right, how can we make that better? A better pattern looks like this in code, but let's look at a graphical representation first. Well, you can do it like that too. It's the same result, it's just a different layout. And well, it's still not a totally efficient thing because still after the first, you lose half of your adaptive work items at each stage. But just in terms of axis layout, this is probably a pretty good. So what can you do to fix this lack of parallelism? Precisely what we need to do. More stuff into each work item. Anything that you might want to look at, you can look at it from an abstract point of view that makes it less clear what's going on. Let's try that. So if you look at, for example, material for these parallel programming systems that came out of Nvidia, so I haven't heard of it. It's kind of cool technology. I'm not sure if it'll work at scale, but PILK. Can't find the markers. If you Google PILK, they prefer to analyze their algorithms in terms of work and span. What is work and span? Work is the total amount of work that we're trying to do. So in the case of reduction, it's we're doing n sum, so n minus 1. And step complexity is how deep the dependencies actually are. And if you divide the two, then you can figure out exactly how parallel your algorithm can be. If you flip through their slides, then you can have upper and lower bounds on your runtime based on that. But we don't have to go there right now, at least. Just what we can see is that our parallelism is kind of bad in the way that we've implemented it. How to improve it? Yes, work item worsening. So last version, what we need to do is not just load one thing up here. Hold on. Oh, those are just index computation. So instead of just loading one, we load a bunch of items until we run out of space, until we've reached the end of the array in a loop, and then we reduce these already summed up things. So this is what this while loop initially here does. Then we have barrier. Then we reduce a couple of times until we reach the boundary of the size of a work group, of a warp, of a SIMD group, at which point we don't have to do barriers at each reduction anymore because things are implicitly synchronous. Beware here, Nvidia says this is fishy. They don't like it. They don't want you to depend on this implicit synchronization feature. And if you ask Mason, he says, oh, you can write a perfectly viable reduction without relying on this feature. I'd be happy to see him show you how all that works, but this is the example that I have right now. Right, so this is the final reduction code. The reason I'm showing you all of this is because I want to include code generation on top of that. Oh, right, here's a performance comparison. So we went from this guy all the way up here to factor of 5 down, and then the last version where we were fully coarsened, then went down by another factor of 5. So that was a pretty nice game. With code generation, what does it look like? Well, so here come in the variables group size, map expression, and reduce expression that we saw, that are pretty much directly given by the user. So, for example, for the dot product, the map was AI times BI, and reduce was just A plus B. And here A plus B gets expanded into whatever gets passed to the C macro. We define reduce, and this becomes the actual reduce expression, whatever we want to reduce on. If we want double support, then we can expand this here. So just this here you could do with something easily pretending that to the kernel that you generate, but this is already an example of where you might want this flexibility, right? And this is, in my opinion, as easy as it gets. Include it on devices that have double support, don't include it on devices that don't. Then type that, okay, I'll type. This just saves me a little bit of typing with the parentheses. Then someone might want to substitute, say, a function definition that they want to use in the reduction expression that might go right out here. Then comes the first bit of actual meat of the implementation. So the kernel gets a name, gets a bunch of arguments, and a bunch of arguments that the user doesn't see. And then we do pretty much exactly the same thing. So we have a neutral element, and then we add up, as in we reduce from the initial read and map down to a width that matches the size of our work group. And then we go from the current size, as in the maximum size of the work item, down to the size where we don't need to synchronize anymore. And we do that by synchronizing, then doing the size computation, the size of the current width of the array to be reduced. And if our work item number is less than that current size, or if it's less than the new size, then we do the reduction. And then in the templating level, we reduce the current size to the new size. So this is a while loop. So this here gets expanded a bunch of times for decreasing sizes. If you were looking back at the initial version that we had, it had all of this hard-coded, as in it had a fixed number of repetitions of this, and it could maximally deal with whatever that implementation could handle. I personally much prefer that, because I can just say, you know, I want my final source code to deal with this many items max, and then it'll generate code for that particular count. Then, lastly, so we get another bit of source code that says if the size at which we can skip synchronization is bigger than 1, the current size is bigger than 1, then we synchronize one last time, and then we do something slightly different where we skip synchronization. Why is it slightly different? Well, we skip synchronization, and it turns out that the least thing that Nvidia expects from you is to access this data through a pointer that has this volatile qualifier on it. Right, and that is the final brace here. That's the end of the reduction. If you guys have questions on that and any of this, I would be happy to take them now. See how we're doing for time. 5 more minutes. Okay. But quick questions on this. Completely overwhelmed? Entirely disgusted? All of you. Good to go. All right. Sounds good. So that shows you a number of different ways in which you can generate code. And in my opinion, it gives you a bunch of flexibility. Yet another way that you can generate code that I haven't mentioned that's available in CUDA is you can do template metaprogramming, where you rely on the C++ compiler's feature that, you know, if you call a function that it can statically resolve and it's marked inline, then ideally it will not produce a call, it will produce an inline copy of it so that you can statically substitute in all kinds of stuff. That, to my mind, is the least appetizing way of generating code. This here is, you know, while you you have to wrap your mind around, you know, what's a templating instruction and what's an actual code flow instruction. The two kind of go along with each other, and so are not too hard to decipher. Whereas there, it's really kind of nasty, and I don't want to diss C++ templates too much. Some of you might like it. Right? Yeah. It's hard to handle. Maybe that one we can agree on. Whereas this here, I personally don't find it too hard to discuss, but it's a matter of taste. Let's not talk about this. Okay. Cool. So I've shown you this. I've shown you an extended case study of how it's used. And in my opinion, this also makes a nice argument for how it's useful, because this can generate a relative relatively large range of stuff from just a single source code without introducing redundancy. Right, yeah, question? Right, this is Mako. I mean, there's no end of templating languages for Python. Choose one that you like, but really they're all kind of equivalent. Mako is as good as it. Right, yeah. So the question was about which templating engine to use or whatever you use, unless you find this particular. If you like if you like hash marks better than percent signs, maybe you want to use one called Ginger. Well, it isn't. Okay, so now you're sitting on this pile of different codes, and you want to somehow evaluate which one you actually want to use, supposing that you're trying to do automated tuning. What do you have at your disposal? Well, we've already seen an example of how to do profiling on a generic OpenCL implementation. You turn on profiling in your command queue, and then you can obtain for each enqueued command an event, and from that event you can obtain exactly when it was submitted to the queue, when it started, and when it ended, and you can thereby figure out how stuff ran. One important thing to note is that on Nvidia CL implementation, as soon as you turn on profiling, the GPU will run synchronously to the host. So if you're trying to do something fancy with overlap communication and stuff, and have this profiling flag turned on, and if you wonder, why is this running so slow? Why am I not seeing the benefits of overlap computation? Well, you're not seeing it because stuff is going synchronous. So it's easy to be tripped up by that, but unfortunately, reality is messy. So rather than use this fancy technology, here's one particular thing that I like. How long do I actually have to wait? Wall time is not such a bad criterion. It's vulnerable, of course, to things going on at the same time, so you need to make sure that your statistics are somewhat robust. But in general, that's what you optimize for. You don't want to wait, so minimize the wait and use that as a metric. You can also look at the compiler build log, for example. The Nvidia compiler will tell you things about how many registers and stuff. And maybe if you're lucky, you'll also have a vendor profiler available to say a few things about the Nvidia one in a few slides. Lastly, one possibility is if you can compute the number of flops per byte, or if you know what occupancy on Nvidia hardware is, you might want to compute those and figure out what they are. Don't give too much by that. But the Nvidia guys say the same thing. Then, given that you maybe now know how you want to evaluate your zoo of different codes, it's always kind of, ideally you only have enough the number of your codes is not too large that exceeds your lunch break. But trying each individual one takes longer than you can walk away from your computer, have a cup of coffee, come back, and you know which one is the best one. Once your search space goes bigger than that, there are a few things you can do. Well, obviously you can just use exhaustive search, in which case it's always easy to add an extra dimension to the search space. The question is which dimensions are actually worth it. That might take some thinking. Alternatively, also if you have a good sense just from observation of what things run fast, which ones don't, then you can add heuristics. Then there's a strategy that I'll explain in an animation on the next slide. Grouped orthogonal search, or you can get arbitrarily fancy. One nice thing is PyCUDA has a compiler cache. PyOpenCL will get one in the next version. The main thing that slows down these searches is that you have to wait for compilation. The actual GPU run will be relatively fast, right? So waiting for the compiler to finish is kind of that's the rate limiting factor. And if you have a compiler cache that's perhaps better implemented than the Apple one, can save you some time. Right. Okay. So it's also going. hour. This group orthogonal search is pretty easy. You have a number of features that you might want to vary, and you define a few possibly overlapping groups. This is, for example, by the way, what Cray used to optimize their sparse kernels. So that's where I started at. Right. So you define a bunch of groups. You pick one of those groups. You write down all the options that you might have, and you just do locally exhaustive search there, and you substitute those back in. And then you go to the next group, you pick another bunch of values, and that way you can cut down the exhaustiveness of your workspace. It's not a brilliant strategy or anything. Probably doesn't even deserve its own fancy name, but it's definitely better than full exhaustiveness. Yeah. Of course.
Some of the more robust optimization strategies.
Right.
I would list those probably before.
Sure. And yes, I flipped through a bunch of papers yesterday, and I found that most of the things people do are up here.
Yeah, I agree.
And it's relatively simple, and if you have one or two heuristics, then you don't suffer too bad. Okay, yes, so we have an expert opinion that says this here is garbage. That's useful information. Right, okay, so but I mean, just think carefully about your search strategy, ask the experts, and perhaps then you'll be asked to go through it again, come up with a nice optimized code. You'll see this in the slides. You can download the slides later. This is how to talk to the Nvidia profiler from within your program and get the data out there. It's also good to know. For the people who are easily appalled by code, this isn't pretty code because it has to work around the fact that the Nvidia profiler writes stuff in batches, but it does the trick. Yes, what can you find out from the Nvidia profiler? You can find out actual memory bandwidth. You can find where you converge it and all kinds of other stuff. And I'll leave this little gimmick for next time. With that, thank you very much for now.